Welcome back, guys. Today we'll be setting the record straight on sets and Venn diagrams. So let's get into it. Before we get into this lesson, let me first take the time to say how much I've missed you guys. Yes, it's been over 2 weeks since our last upload, but guys, I've been so swamped in marking end of year exam papers and writing reports. But now that that's behind me, you can look forward to your regular uploads. Thanks to all of you who have been consistently engaging with the videos. And please continue to support the channel by liking, sharing, and commenting on each lesson. Now, with that being said, let's take a look at sets and Venn diagrams. We will start by looking at some key facts. So first of all, what is a set? A set is a collection of items that are related in some ways. Now, if we think about, for example, a table, a chair, these will be related because they are all fitting in the category of furniture. Talk about roses and daisies and poinsettias are all flowers. So they would make a set because they belong to the set of flowers. Now the key piece of information here is that each item in a set is called an element or a member of the set. Now, how do we represent a set? Sets are always represented using capital letters. So capital letters are often used to represent a set. So for example, if we talk about the set of odd numbers less than 10, we could use the letter A, for example, capital A, to represent this set. It doesn't really matter what letter you use once you write a capital letter. So this is what it would look like. So I'm talking about the set of odd numbers less than 10. I would write that A, capital A, is equal to 1, 3, 5, 7, and 9, which I put in curly brackets to denote this set. Now, what is a Venn diagram? Because we're doing our introduction to sets and Venn diagrams. So when we talk about a Venn diagram, we're talking about a diagram that is a visual representation of the relationships between sets of data. And it uses overlapping circles to show similarities or differences in these sets. So let's look at what this looks like. So here is an example of two sets. So we've got set A and set B. And we can see in the middle we've got 3. So that would be the similarity. And what is in the set, the part of A only and B only, those are the differences. And we'll talk about the rectangle as we go along. So the Venn diagram, importantly to history here, was invented by the English logician that is called John Venn. So this person, you can do a little bit more research on that. Very good to know where some of the content come from that we use in mathematics. So moving along, we can use Venn diagrams to represent a set. So for example, I talked about earlier the set of odd numbers less than 10. Now this is what it looks like if we should put this on a Venn diagram. So we have a solid circle here that represents set A, and within the circle we write 1, 3, 5, 7, 9. So therefore all the elements in A which are in the shaded area represents that set of odd number that is less than 10. And you can see that that circle is within a rectangle. So the outer part of the circle, which is the rectangle, represents all numbers that are not a part of set A. So that's how we would have put this if we were asked to draw a Venn diagram to represent this particular information. Next, we're going to look now at some examples. So we are told to list the elements of each set using the correct set notation. So first of all, we've got A, which is equal to factors of 12. We've got set B, which is equal to months of the year starting with J. C is equal to square numbers below 50. And set D is equal to multiples of 5 that are below 30. So we're going to start by doing part A. So part A asks us for the factors of 12. So first of all, we will need to know what our factors are. Many students tend to mix up our multiples and our factors, but remember, our factors are the numbers that can be divided into a number. So set A then would be equal to, remember, put our curly bracket, the first factor of every number is 1. So 1 goes into 12, we check for 2, 2 goes into 12, 3 goes into 12, 4 goes into 12, 6 goes into 12, and 12 goes into itself. So we look and make sure we've got our factor pair. So we've got 1 and 12. 1 times 12 gives us 12. 2 times 6 gives us 12. 3 times 4 gives us 12. So these are all the factors of 12. So we tick that off. We finish with part A. So part B asks us to give the months of the year starting with J. So we go B is equal to, we've got first month of the year is January. So we list that. Then we've got June and July. And we just put those in our curly bracket. So there are 3 months of the year beginning with the letter J. Check that off. We go to the next question. We're asked to list all square numbers below 50. So C then is equal to, remember, we get a square number when we multiply a number by itself. So we start off with 1. 1 times 1 gives us 1. 2 times 2 gives us 4. So 4 is our second square number. 3 times 3 gives us 9. 4 times 4, 16. 5 times 5, 25. 6 times 6 is 36. 7 times 7 is 49. And we can see we cannot go on to another one because we would have passed the criteria, which is 50. So these are all the square numbers that are below 50. We check that off and we go on to part D. So part D asks us for multiples of 5 that are below 30. And we know that all multiples begin with the number itself. So the first multiple of 5 is 5. So we're counting 5, 10, 15, 20, 25. And we stop because we're asked to do below 30. So those are all the multiples. So we've represented 4 sets. And this is really very simple as we lay our foundation for sets and Venn diagrams. So on we go. So let's look at what we mean when we talk about the complement of a set. So the probability of outcome A occurring is written as P. So the P stands for probability, the probability, and we put in bracket the capital A. So the probability, what if that outcome does not happen? So if an outcome doesn't happen, anything outside of the outcome itself is called the complement of that outcome. So suppose A does not happen. This is written as A dash, which we call a complement, or we could just read it as A dash, or we can call it a complement. So importantly to note, the complement of a set is any member or element that does not belong in that set. It's not a part of the set at all. So the probability of A not happening is written as P, and in bracket we put A dash. So whenever we see A in bracket, probability of A, we are asked to list the outcomes of A happening. However, if we're seeing A dash, it means that we need to list the probability of A not happening at all. And so we're going to look at what this looks like. But this includes all elements that are not in A. So I'll say that again. The complement of any set means all the elements that are not in that particular set. So similarly to how we represented A on a Venn diagram, what then does a complement look like on the Venn diagram? So remember, we put it A in a circle, and all the elements in that circle represent all the elements in set A. Now, if the complement of A is what is not in A, what do you think that Venn diagram is going to look like? So I'm going to put it on the screen and you tell me if that's what you guess in the comment section. So it means then that it's every part of that Venn diagram outside of A that is the complement of A. So all the elements that are in the complement of A, that's what we're shading, which means they are not in the circle. So A dash is everything outside of A, and that's shaded in blue. Important to note that the probability of a set and its complement added together will give us 1, or we could say 100% as well. So I will just visualize it for you. So the probability of A plus the probability of A complement, what's not in A, will always be equal to 1, or it will be equal to 100%. So when we add them together, we will always get one whole. We'll put that in context just a bit more in some questions now. So for example, first example here, ask us to circle the best description of A complement. Remember, A complement is simply what is not in A. So C complement then would be anything that is not C. So our options were C, D, not C, not D. So the answer has to be not C. So the complement of C, and remember, we always look for this little dash, we call it C dash or C complement. So once we see that, we're talking about everything that is not a part of the set C, or whatever letter is it that we were given. So we go to our next question. So we're given here, so this E, I'll come to this in just a moment as we go along to look a little bit more on the universal set. So this Greek symbol here represents the universal set. So we're given 20, 21, 22, 23, 24, 25, 26, and 27. We're told that A is equal to 20, 23, 24, 25, and 26, and we're asked to find A complement. So remember, A complement is what is not in A. So therefore, A complement is equal to, so we look 20, we've got that in the set, so we're going to just tick off all the ones that are in A, and then what's left will be our complement. So we've got 20 in our set, we check 21, not in our set, so that's a part of the complement. So we go for, so let's put a star there, 22, also not in our set, so that's a part of the complement. 23 is in our set, so we don't need that at all. 24 also in our set, 25 in our set, and also 26. So 27 is not a part of our set. So therefore, A complement is 21, 22, and 27. So all the elements that are not in A is A complement. Beautiful. So we go to our third example. So the universal set is 1 to 14, and the set B is 1, 2, 3, 4, 6, and 12, and we're asked to list the members of B complement. So again, all the elements that are not a part of set B. So B complement is equal to, we put our brackets and we check. So 1 is in our set, we don't need that. 2, 3, 4, 5 is not in our set, so we start with 5. We've got 6 in our set, so we don't need that. So we've got 7, that's not a part of our set. 8, 9, 10, 11, 12 is in our set, so we don't need that one at all. And then it's going to be 13 and 14. So all those elements, 5, 7, 8, 9, 10, 11, 13, and 14 are not a part of the set B, so they are the complement of B. So remember, and we always say it, sometimes we say that someone complements us, which means that the skills that we've got, they don't have, or the skills that they have, we don't have. And that's why we come together and put our skills together and make it one beautiful picture. Lovely. Okay, so another example. This time we will do just a small calculation. So we're told here, given that the probability of A is equal to 0.6, we're asked to write down the probability of A complement. So remember earlier we talked about the fact that the probability of an event and its complement add to 1 or 100%. So therefore, if the probability of A is 0.6, the probability of A complement, which is A not happening, would be equal to 1 take away 0.6. So we can just look at this as 100 take away 60, which is 40, and then we can write that as a decimal. So this will give us 0.4. So the probability of A complement or A not happening is 0.4. And to put this in real life context as well, we talk about looking at if we wanted to go like to the park to enjoy ourselves for the day, we always check our app to see what is the probability of like sunshine or rain. So if we see that the probability of rain falling is, let's say, 0.2, we know the probability of rain not falling is going to be 0.8, which means that it is likely that it's not going to rain. So that's one application of these probabilities and complements of sets in real life application. The next question says, given that the probability of A is equal to Tuesday, Wednesday, Thursday, write down the probability of A complement. So we know that there are 7 days in the week. So clearly, if we've got Tuesday, Wednesday, Thursday, then all the other days in the week would be the complement of A. So let's just write it down. So let's start with curly bracket, Sunday, then Monday, so Tuesday, Wednesday, Thursday, so therefore Friday and Saturday will be our other days that are the complement. So we've got 3 there, 4 here. So the complement is Sunday, Monday, Friday, and Saturday. So they were not in the set A, and those are the rest of the days of the week. Amazing. So now we're going to look at the universal set. So when we talk about the universal set, it contains all the elements that we either use in our question, or if we talk about the universal set on a broader scale, we're looking at the general set from which all other sets are taken. So if I talk about the set of alphabet, from the alphabet I can get vowels and I can also get consonants. Therefore, if I wanted to spell my name, the universal set from which I would get my letters would be the alphabet. So the alphabet is an example of a universal set. Counting numbers is also another example. From counting numbers, we can get prime numbers, odd numbers, square number, cube numbers, and so on. So those are examples of a universal set. The set of flowers I mentioned before, you can get roses, daisies, and all other different kinds of flowers. So flowers in general can also be considered as a universal set. So importantly here, we use this Greek symbol, which I mentioned before, to represent the universal set. So diagrammatically, if we draw a universal set, I've shown you before, we always put the little symbol here on the outside to show that everything thing in the rectangle will represent the universal set. So let's look at what this means here. So if the universal set, for example, is equal to multiples of 3, if I have a set A, which is 30, 60, and 90, those are just a few of the multiples I could get from the entire universal set. So when I pick a set out of the universal set, a smaller set, that set is called a subset of the universal set. So it is a subset, a smaller set. So 30, 60, and 90 are a subset of the universal set, which represents all multiples of 3 from 3 all the way to infinity. Okay, so smaller sets. Now we're going to look at 2 sets of examples and then we're going to summarize. Okay, so we're given the universal set here and we're told that the elements or members of this set are 10 to 100. Now we've got some questions to answer from the universal set. So we are asked to list the elements of set A, B, and C from the set given above. So first question asks us to, A is the factors of 100. So we want to find what are the elements of set A. So A is equal to, remember, put that in curly brackets. So factors of 100 are 10. Then we've got 20, 30, 40, not factors, 50 is a factor, and also all the way over to 100. So you can see here, in order to do Venn diagrams accurately or anything concerning sets, we also have to know some other key factors. We need to know what are factors, what are multiples, what are square numbers, and so on, based on what we could possibly be asked. Now for the next question, ask us the B is equal to square numbers. So again, in the previous question, we looked at something concerning square numbers. So remember, square number we get from multiplying a number by itself. The product or the result is a square number. So for example, 1 times 1 is 1. So 1 is a square number. 2 times 2 is 4, so 4 is a square number. Now if we look here, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. The only square number here is 100, since 10 times 10 gives us 100. So only one element or member of this set. So the next question is part C, asks us to give multiples of 8. Remember, every multiple of a number begin with the number itself. So we start with 8, but there's no 8 here. So 16 and so on. So basically, we're looking for numbers that are on the 8 times table. So we look in our list, we've got 10, 20, 30, 40. So 40 is our first number on the 8 times table. We've got 50, 60, 70, 80. 80 is the second and last number on the 8 times table from this particular universal set that we were given. And finally, we go for part D. Part D asks us to list the elements. So the set D contains prime numbers. So remember, a prime number has only 2 factors, 1 and itself. And the first prime number is 2. And the only uniqueness about that number is that it's the only even number that's a prime number. So we check here. We've got 10, 20, 30, 40, 50, 60, 70, 80, 90. All these numbers have more than 2 factors. So in our list, there are no numbers that are prime numbers. So how do we represent this? So this is called the null or empty set. So I'll just write that here. So null or empty set. So to represent that, all we need to do is to put our curly brackets, and there will be nothing inside those curly brackets. So when there are no elements in a set, we just write our curly brackets to show, and leave it empty to show that no elements found in this set. So thank you for getting so far. I'm so proud of you. So now we're going to do our last example, and then we're going to wrap this up. By the way, have you remembered to like the video yet? If not, give it a thumbs up. Okay, so last set of example, we're given another universal set here, and we're given number from 1 to 10, and we're told that set A is odd numbers and set B is the factors of 12. So in part A, we're asked to list the elements of set A. In part B, we're asked to list the elements of set B. And in part C, we're asked to list the elements that are in both A and B. A beautiful way to end our question, as it leads us into a higher stage of sets and Venn diagrams when we get into our next part of our Venn diagrams series. Beautiful. So we look and we observe, we're asked to list all the odd numbers. So A then would be equal to, our first odd number is 1, then we've got 3, then we've got 5, we've got 7 and 9. So those are the elements of set A. For set B, we are asked to list the elements which are factors of 12. So B is equal to factors of 12. First factor of 12 is 1. We also have 2 can go into 12. 3 goes into 12. 4 goes into 12, not 5, but 6. And then we check 7, 8, 9, and 10, not factors. So these are the only factors of 12 from the universal set that we were given. So we go to the final section of the question, which asks us to list the elements that are in both A and B. So in set A, in set B, we check. We've got 1 here, 1 there, so it will be 1. We check 3 in this one. There's also 3 in the other one, so we check that off. So, comma, 3. Then we've got 5, 7, 9. In the other set, we have 2, 4, and 6. So the only elements in both set A and set B is 1 and 3. Beautiful. So we're going to pick up from here whenever we release our next lesson in the Sets and Venn Diagrams series. So leads me to the point to ask, what is your key takeaway? So what are you taking away from this introduction to Sets and Venn Diagram? So the first thing we talked about was that a set is a collection of items that are related in some way. We also talked about the fact that each item in the set is called an element or a member of the set. We talked about the fact that we represent a set using a capital letter. Really doesn't matter what letter it is. We also looked at the complement of a set, which means elements that are not in a set. Okay, we talked about how to represent that. We write our capital letter with a dash, and that tells us that that's the complement of that set. Now, we also mentioned that a set and its complement, when added together, will always be equal to 1 or 100%. We looked at the universal set, and we said the universal set is the set from which all other sets are taken. We mentioned the letters of the alphabet. You could also talk about the months of the year, counting numbers, set of flowers, and so on. Now, when you take a set out of the universal set, a smaller set, that's called a subset. And we looked at some elements of subsets as well. Absolutely fantastic. Now, Thank you so much for watching this all the way through, and also thank you for putting a like on that video. And remember, we are also on TikTok. It's a good idea to go there and watch all the videos that are there so far, and make sure that you continue to practice, even though you may now be on summer break by the time you see this video. Well, make sure that you continue to revise. So guys, thank you so much for watching.